then continue from yesterday. So let me just close this. Well, all right, so we kind of do this. So yesterday we got as far as working out this average over the fast degrees of freedom of the second order in this dimensionless coupling constant contribution to the effective action. And what we had obtained was this was some numerical coefficient which was related to this cutoff function which I called f of x. And precisely what this coefficient here is depends on the scheme. So it's an integral over this f function. It's just some number. And then here we had beta squared over 4 pi squared dl. And then here we had d squared r. So the integral over the center of mass coordinate grad r phi lambda prime squared. So this is a contribution to the effective action which renormalizes the Gaussian part. Yeah. So now the full effective action. So before rescaling space and time again, looks like this. So we have the Gaussian part, d squared x grad phi lambda prime squared. And now here we have the 0th order term, a half, and then we have this piece plus lambda squared divided by 2a beta squared over 4 pi squared dl. So something like this. And then we still have the first order contribution, which we worked out before, which was proportional to lambda, not lambda squared. And this was lambda 1 minus beta squared dl divided by 4 pi integral d squared x cosine beta lambda prime. So something like this. So this is basically as far as we got yesterday. And then in order to complete this RG step again, we again have to rescale. Space goes to lambda prime over lambda space. And momentum goes in the opposite direction, goes to lambda divided by lambda prime k. And this then gives us the full action. Do I really want to write it again? No. So I will just modify this formula. So when I rescale, I get the effective action, but now I have rescaled to recover the original cutoff, so it depends on phi lambda. Now the Gaussian part is scale invariant, so this piece just will retain its form. And here, as we had already seen yesterday, we get this extra contribution. So we had plus lambda, and here we have 1 plus 2 minus beta squared over 4 pi dl. So this is the result of the second order calculation. Right? The first order calculation gave us just this rescaled cosine term. Nothing happens to this. And in the second order contribution, two things happened. We pick up this extra contribution to the Gaussian part of the action. which will be very important. And then, as we had seen yesterday, there was also this higher harmonic. Yeah, there was a term which was like cosine, not beta phi, but 2 beta phi. Yeah, and then I argued for you, I can drop this. Yeah, because the scaling dimension is very, very large of that perturbation. So it's an irrelevant contribution. So I have just discarded it. Yeah, but it is in principle there. Okay. So now we want to deal with this renormalization of the Gaussian part of the action. So this, in order to deal with this, we have to introduce a multiplicative renormalization of the field. So multiplicative renormalization of the field. So phi lambda has to go to, I introduce the z factor, square root of z phi lambda. Yeah. And once I do that, I see here in the cosine term, I also have to multiplicatively renormalize beta, yeah, in order to compensate the field renormalization. So in order to keep my get the correct cosine term, I have to renormalize beta like 1 over square root of z beta. Okay, so this is what we do. And z, the z factor here is precisely what I have there. So it's 1 minus lambda squared divided by 2 a beta squared divided by 4 pi squared dl. Yeah, so it's the inverse of what I have written there, using again that dl is small. Okay, so this is interesting. So now both lambda, so little lambda, so this small coupling constant, but also beta become L dependent. Yeah. So in other words, to second order in this RG procedure, not only does the coupling constant run, but also beta runs. Sorry, you're looking at this? No, it's okay, because there is a dl. dl squared is 0. Yeah, and so basically, I'm taking this factor I have there, and I want to absorb it by the field renormalization, such that the coefficient again becomes a half. And I hope I did this correctly. Sorry? But the 1/2 remains. Yeah, so the normalization, so let me just see. Let me just see whether I did this correctly. So you have to be careful, because you pick up a factor of z squared, yes? You understand this? Sorry, not the way I've done it. So I've did, yeah, okay. So then let me just see. 1/2, 1, this, and now I take square root of z, which would give me the factor of Just a sec. So it's I pick up Z, and then I probably don't need this factor of 2. That was your comment, yeah? Okay. Thank you. Okay. Yeah, which is what I have written here. Okay, great. So that was just a typo. Okay. So now, what we want to do is we want to write the RGE equations. So again, we want to compute d lambda dl and d beta dl, and we could do that. But it's convenient at this point to change variables for these two coupling constants. So I have two coupling constants, beta and lambda. So instead of these, it's customary to define two coupling constants z parallel, which is beta squared over 4 pi minus 2, and z perp we define to be square root of 8a lambda. Okay, so that's just a change of variables. So when we do that, the RG equations take very nice forms, and importantly, this number a, which is scheme dependent, which I don't really know, disappears, and we get the equations dz parallel dl is equal minus z perp squared, and dz perp dl is minus z perp z parallel. Okay, and so these are very famous RG equations. So these are called Kosterlitz-Thouless RG equations. Okay, and by analyzing these equations, which I'm going to do now, we will understand what this cosine perturbation does to second order in RG. Okay. So now, if you look at the flow diagram, RG flow diagram, so we write here Z parallel, here Z perp, and so here would, well, let's do it like this actually. Let's just look at half of it. So here is 0. Yeah. Then we can depict the solution to these differential equations in terms of an RG flow. It looks like this, so let me draw it first. Here we have this, and then here we have stuff like this, and then here we have stuff like this, and here we have stuff like this. The way to read this is if you start with some initial values of beta and lambda, yeah. So this positions you at one of these trajectories. So let's say at this one here, yeah. And then you integrate the RG equation. So you integrate out the fast degrees of freedom, and your coupling constants renormalize. And what the RG flow diagram tells you, the coupling constants Z parallel and Z perp, they flow following this trajectory. Yeah. So if my initial conditions, yeah, initial value of lambda and initial value of beta are such that I'm here, yeah, then Z perp actually goes to 0, yeah, and Z parallel goes to some finite value. Okay, and what we had to first order, let me contrast this with the analogous flow diagram we had to first order. So the analog of Z parallel, so this was just beta squared divided by 4 pi minus 2. Yeah, and Z perp was basically lambda. And the first order flow equations were just if beta squared was less than 8 pi, I was going to strong coupling. So I had something like this. And if beta squared over 4 pi was larger than 2, the perturbation was irrelevant. So we had an RG flow like so. Okay, that was first order, and now we have second order. And the important result, so one of the important results of Kosterlitz-Thouless essentially is when beta squared is close to 8 pi, then the second order in the RG modifies the RG flow very significantly. On the other hand, if we are here, let's say, you see the RG flow when you have a very relevant perturbation is still essentially just a vertical increase, so it's just like the first order calculation. Similarly, here, the perturbation actually would be irrelevant, and you see this flow is almost like in first order. And the main modification is close to beta squared equals 8 pi. Okay. So now there are three regimes here. So the first regime is when Z parallel is larger than Z perp absolute value. So this is what's called the weak coupling regime. And this is critical. Yeah, and that's the one relevant to what we're going to do when we're going to do bosonization. So there basically you're in this regime here. Yeah, and you see your cosine perturbation basically flows to Z perp is equal to 0, and Z perp is like lambda, which means you get a cosine perturbation with some value of beta, which is essentially given by this Z parallel, but the running coupling constant in front just goes to 0. So that means these cosine perturbations, they're irrelevant, they don't affect the low energy physics, and you remain critical. Yeah? And so this is what we're going to exploit. Now there are two other regimes. There is the so-called crossover sector. So there I have minus Z perp less than Z parallel less than Z perp. So that's the crossover sector. So here the flow is eventually to a strong coupling finite correlation length regime. But so this RG flow can take a long time. So you basically are on trajectories like this one here. So you see initially, like your coupling constant lambda actually goes down. It almost looks like the perturbation is irrelevant, but then eventually it starts growing again and diverges, yeah, becomes order 1, and you generate a finite correlation length. Now, this RG time here, you should think, so what you're doing is you integrate out degrees of freedom, yeah? And so the RG time is basically related to some kind of scale on which you look at correlations. So then here, initially, you have the starting point, which is in the ultraviolet. So you're looking at the short distance physics, yeah? And then the short distance physics in this model, it always looks like a power law by construction. So then for these kinds of flows, initially, it looks like you retain a power law. So the perturbation almost looks like it's irrelevant. But then if you look at larger and larger distances, so in lower and lower energies, eventually you see there is a finite correlation length. So if you were on such a regime for the lattice model and you would look at a two-point function of some spin operators, you basically would have to go to very large separations to see a finite correlation length. So the correlation length would be very large, so to speak. Here, yeah. And the third regime is just this one here, where you just have a relevant perturbation. So this is Z parallel less than minus Z perp. And so this is the strong coupling. And so here the flow is immediately towards strong coupling. Yeah, so you have a finite correlation length, but what you can do now, which I'm not going to do because it would take me too much time, you can again estimate the correlation length, yeah, in terms of your RG flow, and the results for the strong coupling sector and the crossover sector, they are different. Yeah. Yeah. Yes. Yeah, okay, so it's a very good question. So we do things to second order for a reason, because in this business, if you go to higher orders, it becomes more and more messy, right? So typically we go to second order, so this is a standard calculation. So what I show you here, it's a standard calculation. And there, in a sense, by going to this Z parallel, Z perp parameters, you can remove the regularization scheme dependence. Yeah, but this is no longer true for the higher orders. So the precise RG equations you get, they will depend in detail on the scheme you use. But the physical picture, this is what you're asking, so kind of the phase diagram that you get out of this RG flow, that remains the same. Easily, no, if it could be seen easily, I would tell you. I would show you how it's done. Yeah, but people have gone to higher orders, first of all, right? So that is one thing. And another thing you can do is, so this is some kind of like universal behavior at large scales that applies to a large class of different models. So in particular for these lattice models I'm going to introduce next. And you can compare, so some of these lattice models are exactly solvable. Yeah, I'm not going to talk about that. So you can compare the results you get, exact results you get for the lattice model to the RG flow, and it fits perfectly. Yeah, so this is really all you need to know. Okay, but people do go to higher orders, but it becomes a lot more complicated. Yeah. So in terms of you can reformulate all of this if you like diagrams. In terms of diagrams, Yeah, so this is essentially a one-loop calculation, but then you want to go to higher orders, it's 2-loop, 3-loop, 4-loop, and then if we ever have done a 2-loop calculation, you will know you don't want to do that. Yeah. Okay. I haven't actually, so I skipped over this. In my flow diagram, I restricted it, but you see here, I allow Z perp to have either sign. So basically, if you go to negative, you just copy, yeah. Yeah, I mean, so this is a question I can't answer very easily. I mean, so how to translate RG time into some physical observable light is not something I want to discuss actually. So ask me afterwards if you want. Yes, absolutely. I mean, so this you can see this kind of behavior in particular lattice models. I mean, so essentially, you need a model, yeah, where your parameters work out that initially your bare coupling constant, so your initial value of lambda, initial value of beta, are such that you're above this line here. This line is called the separatrix. There's something very special happens. There's some additional symmetry, so there's always a U1 symmetry in this problem, but on the separatrix it's actually enhanced to SU2. I'm not going to discuss why that is. But so you need a model where you're above, and this is perfectly fine. So such models are known. Yeah? Okay, that's all I really wanted to say about this Wilsonian RG. The way I will use it, I will not use any of the details of what I've shown you, but everybody needs to have seen this Kosterlitz-Thouless RG flow once in their lives. So now, if you hadn't seen it before, you have seen it now. We will use the main message from this calculation from here onwards. And the main message is, if I have a free boson, which was my free action, and if I perturb it by a cosine term, yeah, or many cosine terms, if you wish, then in many circumstances, I can just forget about all of these perturbations because they will be irrelevant in the RG sense. And if I look at low enough energies, large enough distances, I don't have to worry about them. Yeah, and so the proper description of the low energy physics will just be a free theory, the free boson theory. That is what we're going to use this for. Yeah. So, and the cases where the cosine is relevant, yeah, if I have time, I might give you some example of that as well. The only message we will take away from what we have done here is then there's a finite correlation length. You're no longer in a quantum critical regime. It's a fully interacting theory, so life is more complicated. Yeah, so that's what I want to use this for. But this whole bosonization approach, it cannot really be understood without having this in the background. Yeah. Okay, so now we're going to leave this behind and basically start something which is on the face of it entirely different. So in the first lecture, I had told you about this Heisenberg spin half chain. So now we will actually get back to that and spend a little bit of time first of all, understanding some simple things about this Heisenberg chain, and then we will construct the low energy field theory limit and relate it to the free boson. Okay, so this is what we're going to do next. So the first step in this is, okay, so the Heisenberg model was something like this. Okay, and now in order to proceed, we map this, which can be done exactly on the lattice in one dimension, to a model of interacting fermions. And this is done by something that's called the Jordan-Wigner transformation. And that is an extremely useful tool in one dimension. So the idea is very simple. So first, remember, the raising-lowering operators of spins are just defined as xj plus minus I syj. And now we define operators, which I call little cj, is product L equals 1 to j minus 1 to szj, and then here I put an s minus j. Okay? And then, of course, there's also the Hermitian conjugate to this operator, so that I call C dagger J, obviously. Now, the interesting observation is that these fulfill canonical anti-commutation relations. So in other words, Cj anti-commutes with Cl, and the anti-commutator Cj with C dagger L is delta JL. So in other words, the operators I've constructed there, or Jordan-Wigner have constructed, they are spinless fermion operators. Yeah? And there is an inverse transformation. So this is a one-to-one map, and the inverse transformation is simply Szj is C dagger J Cj minus a half, and S minus J is product L equals 1 to J minus 1 to C dagger L Cl minus 1 Cj. And then this is quite often written in terms of an exponential form, L equals 1 to J minus 1, C dagger L Cl minus 1, Cj. Okay? Ouch. Okay, just a quick question. How do you see that this, well, it's called the Jordan-Wigner string operator, is equal to this? So how do you see that 2 C dagger L Cl minus 1 is the same as e to the I pi C dagger L Cl minus 1? Yeah, you can do it that way. It's not the simplest way. This is the simplest way. There are basically two states, the vacuum and the occupied state. If you act here on the vacuum, this one annihilates it, you get minus 1. And on this one, you get plus 1. Yeah, and here, this is an eigenstate of this. Yeah, so again, this annihilates it, so you get minus e to the minus I pi. Yeah, which is minus 1. On the other hand, if you act on this, It's an eigenstate with eigenvalue 1, so you get e to the 0 times I pi, which is 1. Okay, so it's indeed correct. All right. Anyway, so that's probably too much detail. So now we apply this to the Heisenberg Hamiltonian. So let me just, I call this H of delta H. And I will assume, just for definiteness, that L is even, yeah. For L equals odd, some weird and kind of not entirely uninteresting things happen, but life is short. So we will focus on even length of the lattice. So now we apply this Jordan-Wigner transformation, and that gives us an expression of the Hamiltonian in terms of the spinless fermions, and it takes the following form. So we have this, then we have the magnetic field term, and last but not least, there is the interesting part, C dagger L C1 e to the minus I pi L equals 1 to L and L minus 1 plus Hermitian conjugate. Yeah, so N, I should have said, so I call Nj, I define C dagger J, Cj. Okay, so now, so you have to, okay, so observe that this term here looks a little bit weird, right? Because it looks like it's non-local, etc., etc. Where does it come from? Well, it comes from the fact that these spinless fermion operators, they involve a string of spins, if you wish, that starts at position 1 and then extends, or this is a better one. So the spin operator has the Jordan-Wigner string that starts at the first side and then goes to the J minus first side. And if you have an interaction, let's say S dagger S plus L S minus 1, yeah, which is one of the terms I have because I have periodic boundary conditions. Yeah, so the neighbor to the L side is the first side. So you see that this guy involves the Jordan-Wigner string all the way down to the first side. So in terms of these spinless fermions, these have to be non-local, involve the entire string. That's this baby here. Sorry? I have taken one additional step and made it L. So, a priori, it's L minus 1, okay? But then I would have the opposite sign here, essentially. Then I can flip the sign by putting this. Yeah? So, I'm not sure whether you can see that. No? So, you see, so C dagger L e to the minus I pi n L minus 1, yeah, is essentially, there's a minus sign which comes from here. Then I have something like this. Okay? But now, NL to any power is NL. Yeah? And so this is just minus C dagger L, because in NL I have a C dagger L, and C dagger L is 0. Yeah? So I could have written this like so, but I don't like it because I want to use this in the next step, which is why I have changed the sign and put the extra factor. Yes? Okay? So now this looks kind of nasty at first sight, but actually it's not. Yeah, so this is very simple to deal with. So we can rewrite this string term here as j over 2 c dagger L C1 e to the, sorry, I have minus 1 to the n, because now you see L is even, so I get a e to the minus I pi L, which is 1. So the only term that remains is e to the minus I pi, the sum over all L and L, but that's just a total particle number, total number of spinless fermions, which I call n hat, plus Hermitian conjugate. Okay? Now, recall that the Hamiltonian actually, as I stressed, had this U1 symmetry, so it commuted with SZ. Okay? And that translates that the Hamiltonian actually commutes with the total number of fermions. Yeah, you can see this also quite easily because number operators, of course, don't change the number of fermions. In the kinetic energy term, I don't change the number of fermions because I destroy one, but I create another one. Yeah, and here it's the same. I destroy one, but I create another one, so I don't change the number of fermions. Okay, so the Hamiltonian commutes with total number of fermions, which means H is block diagonal I can basically write it like so: H even, H odd is block diagonal in the sectors, or with respect to the sectors of even odd fermion number. Okay? So this means we can write the Hamiltonian in a very nice form. H of delta H is in fact minus j over 2 sum j equals 1 to L C dagger j Cj plus 1 plus Hermitian conjugate. So we have this plus j delta sum j nj plus 1 plus H minus j delta sum over j nj plus a constant with one caveat, which I'm going to write down now. So the one caveat is that the boundary conditions on the fermions now depend on whether there's an even number of fermions or an odd number of fermions. So Cl plus 1 is either plus or minus C1. Yeah? Or in terms of n, I write it like so. And that means we have periodic boundary conditions for n odd and anti-periodic boundary conditions for n even. And n is the number of fermions. Yeah. Yes, as I said this twice, L is even. Yeah. Yeah. Okay. All right. So now we are back in business. Yeah. So we have mapped the spin Hamiltonian to the spinless fermion Hamiltonian. Okay. So we have got rid of the spins, which are not as nice as spinless fermions. And the one price we had to pay is we have to consider two sectors of boundary conditions, yeah, periodic or antiperiodic, and which ones I am supposed to use depends on how many fermions I have in my states. No, because so let's see. No, okay, so this is certainly correct. So for n odd, I want 2 pi n of L. So no, this is correct. Now, what you have to remember is that this comes with a plus sign, and I have a minus sign here. Yeah. So this explains. Okay. Now, okay, so what I'm going to do next is I'm going to show you actually how this works out in practice, and you'll see it's not a big deal. All right? Any questions so far? No. Okay. So now we're going to learn something kind of interesting, which is very, very simple but very useful. So let's look at this XXZ chain at delta equal to 0. So if I set delta equal to 0, I don't have this term. Yeah. So I don't have the interaction term. So I get a Hamiltonian, which is in fact quadratic in fermions. So H of 0H is quadratic in fermions. So it's a free theory. So we can diagonalize it by Fourier transform. Or by going to modes. And as I said, so this is kind of very nice, because if you didn't know anything about anything and somebody showed you this spin Hamiltonian, you wouldn't have guessed that this is equivalent, or this can be mapped one-to-one on a model of non-interacting fermions. And then, of course, for the model of non-interacting fermions, you can compute a lot of stuff quite easily, which is not so easy to compute at the level of the spins. Okay, so now what we want to do is we want to say, we want to define Fourier modes. So we define C of Kn is j equals 1 to L Cj e to the I Knj, and I'll stop in a moment. And you can easily check these fulfill canonical anti-commutation relations like so. L delta Nm. Yeah, and observe I've chosen the definition in such a way there's the L here, and I do this so that once I take the continuum limit, I get a delta function. And now if I have periodic boundary conditions, Kn is just 2 pi n over L, and so minus L over 2 less than n less than L over 2. Whereas if I have antiperiodic boundary conditions, Kn is 2 pi over L n plus a half. And we would have the same here. So this is where the difference comes in. Okay. So now, just 30 seconds. Yeah, so Pasquale is already ready to run. Now, in both the sector where I have periodic boundary conditions and anti-periodic boundary conditions, so in terms of the two sectors where the particle number is fixed, I'm going to write this down after the break. The Hamiltonian now will be very simple. Will be just some dispersion relation times the number operator in momentum space. So it will be very simple here. It will be very simple here. We'll have the same form. The only difference being what values for Kn I'm summing over. But of course, the relation between these two is complicated. Yeah, because in order to work that out, you would have to ask the question, how is C of Kn when Kn takes this value related to C of Kn when Kn takes this value? And that relationship is very non-trivial. Okay? And so that's a caveat you have to keep in mind. So within the sectors where the particle number is fixed, everything is easy. But as soon as you start dealing with stuff where that involves going from one sector to the other, etc., you have to worry. Okay? And with that cheerful thought, I leave you to your 10-minute break. All right, so I've been told I should carry on. Okay, so this might be a little bit early for you guys, but so one of the interesting things about Wigner actually was, so he won the Nobel Prize in physics, but he didn't get tenure at Princeton. So, and I think that probably one should tell everybody, so it haunts them to this day. So the Hamiltonian in momentum space, I can write like this. In either sector, and so this I call the dispersion relation. Yeah, so this comes out by just doing the Fourier transform, so going to Fourier modes. Okay, and this is valid both for even n and odd n, and the place where whether I have an even number of electrons or of fermions or an odd number of fermions enters is just in whether these k's are 2 pi n over L or 2 pi n plus a half over L. Okay, and then I had the same question twice in the break. Where people were saying, well, the Hamiltonian is not just block diagonal with respect to even and odd fermion number, but with fermion number per se. So I had written the Hamiltonian like in these two blocks, H even, H odd. And then, of course, the Hamiltonian is block diagonal in both of these blocks because it commutes with n. But in the blocks, the Hamiltonian is of this form. This is just n of Kn, the number operator. And of course, these number operators commute for different Kns. And these are your blocks. Yeah? So yes, it's true, but it's not something you have to lose sleep over because it's kind of very, very simple. Okay. So we have this. Now, this already teaches us something which is not to be sneered at. So this gives us easy access to a part of this phase diagram of the Heisenberg model. So I had these two parameters, h and delta, yeah, and here was delta equal to 0. And so I had drawn something like this. And so this very simple map, using the Jordan-Wigner transformation, now tells us everything we want to know on this line. Okay? And what's interesting about this, that includes one of the two phase transitions, quantum phase transitions in this spin chain. Namely the one that happens along this line, which I call the commensurate-incommensurate transition. And what we can do now is we can basically understand what is the nature of that quantum phase transition, and it's very, very simple, and this already tells us what the nature is. So there are two phases for h larger than j. Just look at this dispersion relation, then epsilon of kn is always positive. And this tells us that the ground state is just the fermion vacuum. Yeah? And again, I will have one fermion vacuum if I have an even fermion number and a different fermion vacuum if I have an odd fermion number, so to speak, in the problem. Oops, sorry. So all excitations have a gap here. Okay, so that tells us what the large field phase is like in terms of the spins. It's just a ferromagnet where all spins basically point in z direction. Okay, and flipping a spin costs a finite energy. And the other regime is h between 0 and j. So there we must fill the Fermi C. Yeah, so epsilon of k looks something like this. Yeah. This thing, and so here might be pi, this might be minus pi, here would be epsilon of k, this would be k, yeah, and I have to fill all negative energy states, that gives me the ground state, and the negative energy states, they occur here, and I have to fill between what I call kf and minus kf. So kf is obtained by epsilon of kf is equal to 0. Yeah, so that tells me kf is arc cos h over j. So that's the Fermi momentum. And the ground state then is obtained as a Fock state where I take the product of all of these momenta, kn less than kf, c dagger of kn on the vacuum. Okay, and depending precisely how I tune the magnetic field, I might have an odd number or an even number of fermions in the ground state. Let's assume it's an even number. Okay? So what is this commensurate-incommensurate transition then? Well, it's a transition between a ground state, which is a Fermi C, and a ground state, which is the fermion vacuum, yeah, with gap-full excitations. Okay, so now the interesting part is in this regime here, the correlation functions are power laws. So for example, if I look at the density-density correlator, so this takes the form kf over pi squared plus kf over pi delta L0 minus 4 sine squared kfl divided by 2 pi L squared. Okay, so it's a power law. Yeah, so they're long-range correlations, and they're modulated, so they oscillate, yeah, with a wave number that's related to the Fermi momentum. So an exercise is show this. Yeah, so it's very simple. So you basically just write the n's in terms of the c's and c daggers, and then the cj and c dagger j you express in terms of the c of k's, yeah, and then how the c of k's act on the ground state, you know. Okay, and once you do that, you get this answer. Okay, so now why do I look at the density-density correlator? I look at the density-density correlator for a reason. So recall that SZJ was just NJ minus a half. So in other words, this tells me what the density, the SZ correlation function does in the spin model. Okay? Okay, so now what about this commensurate incommensurate transition? Okay, so for H less than J, we have the correlations oscillate with 2kF, and so that in general is incommensurate with the underlying lattice. Yeah, so what I mean by that is if you look at the separation between the two ends of the two spin operators, you have a factor which goes like e to the 2I kfl. Yeah, and then in general, this will be a phase which is something. But if you increase the distance by one lattice side, this will just be another phase, and then another phase, and then another phase. So this is not -1 or e to the I pi, it's not I to some power. That's what I mean by incommensurate. Okay, so this is what in the other phase, H larger than J, correlations do not involve such oscillations. Yeah, and this is where the name comes from. So incommensurate to commensurate transition, also known as Pokovsky-Talapov-Japaridze-Nersessian transition. Okay, and now let me just say the following thing. So along this line, the transition is very simple. It corresponds to having a Fermi C, yeah, that you empty out by increasing the magnetic field. So the Fermi C becomes shallower and shallower and shallower until at the transition point you empty it out, yeah, and you're dealing with a non-relativistic theory, so with a nonlinear, with a quadratic dispersion, yeah, that is gapless. Okay, And now you might ask, well, what happens if I have interaction, so if delta is not equal to 0. So here it's just a free fermion transition, a very simple free fermion transition corresponding to empty out the Fermi C. So now if you put interactions, you can basically convince yourself they will not change this free fermion nature of the transition. The reason is simply the transition occurs where the density of fermions in the ground state is 0. Yeah, so you basically have very few fermions sloshing around. So it's very, very dilute system of fermions. And therefore, interactions will not play a role, yeah, because you have very few fermions. So the likelihood that they're sitting next to one another and therefore can interact with the interaction strength delta, which is nj plus 1, is very low. Okay, so therefore, it turns out the nature of this transition across the entire line is always like a free fermion transition. So the critical exponents are the same as the critical exponents calculated here, which you already can do by this very simple calculation. Okay? Now, the last thing I want to say now is, so here I basically told you the SZ correlator we can calculate very easily. Yeah, and the reason is SZ is basically proportional to Nj, and Nj does not change the fermion parity. Okay, because it's a C and a C dagger. Now, if you were interested in correlation functions of the transverse components of the spins, so these you cannot calculate easily. Yeah, so this back of the envelope calculation that gives you the answer I had written there does not apply. It's because this correlation function, if you map it to fermions, it involves a Jordan-Wigner string. Yeah, and you still can work it out, but it's a little bit harder. And it's not subject of these lectures, so I will not do it for you. But you can look, for example, in this paper by Vaidya and Tracy, Physica 92A 19078. Yeah, so basically what you can do is you can express this correlation function in terms of determinant, and then you can work out what is the asymptotics of the determinant. Okay, good. So now that's all I'm going to say about this. No, okay. So I'm going to say one more thing actually. Okay. Okay, so now what we have is we have this model of spinless fermions with two sectors, periodic, antiperiodic boundary condition. Okay, what I want to do next is I want to show you that the low energy sector of that theory is equivalent to the free boson that we studied 2 days ago. Okay, so in order to motivate this, remember that for the free boson, I had written the full set of finite energies in the finite volume. I had given you all the energy eigenvalues of the free compact boson and all the momentum eigenvalues of the free compact boson. What I'm going to do now is I'm going to compute for you the energy eigenvalues of this free fermions with the two sectors and the momentum eigenvalues of the free fermion with the two sectors, and you'll see they're exactly the same as the one for the free boson. And this basically then suggests the two theories are the same, and then we kind of will establish precisely how the correspondence works. So let's look at the finite size spectrum. Of low-lying excitations. Okay, so let's take, to begin, so L we take always even, yeah? So from the beginning, what I will do now is I will start with taking the number of fermions to be odd, yeah? And I'm going to tell you what happens with even fermion number later. But I will fix the density n over L. I take this fixed, and I'm interested in having in the length of the lattice being very large, and n being very large, yeah, but d being precisely fixed, yeah. So that basically means you start with L equals 100 or something, and let's say you have 25 fermions, and then you consider a sequence of lattice lengths. You double L, you double N, so that the density is exactly the same in this sequence of L's and N's you consider. And this is very important, yeah, so that you keep this exactly the same. Okay, now N odd tells me that Kn is 2 pi n over L. Yeah, and then we had written this before, minus L over 2 less than N less than L over 2. Okay, and now you see this periodic versus periodic boundary conditions, it works out precisely in the way you like it, because n is odd, so the kn's are 2 pi integer over L, so I will have n equal to 0, n equals to 1, n equals to minus 1, and so on and so forth. So if I fill the Fermi C, yeah, when Kn take this 2 pi integer over L values, the Fermi C always will involve an odd number of fermions, yeah, which is why this choice is the right one, so to speak. Whereas if n was even, yeah, so you don't have 0 momentum, so you start with n equals minus a half and n equals plus a half. So again, you can nicely fill a Fermi C. Yeah, and so this was in response to some comment we had earlier suggesting that periodic versus antiperiodic should be the other way around. Okay, now what we want to consider first is the ground state energy. So E ground state is n equals minus n minus 1 over 2, n minus 1 over 2. N is odd, so n minus 1 is even, so n minus 1 over 2 is an integer. And then here we have minus j cosine kn plus h. So that would be the ground state energy where I have filled all the negative energy states. Okay. So now what we want to do is we're interested in this regime where L becomes humongous, N becomes humongous, and the ratio N over L is fixed. Okay? And in that limit, we can, of course, turn the sum into an integral and then do an asymptotic expansion in powers of 1 over L. Yeah? That's what I want to do. Next, we do this by just the standard Euler-Maclaurin formula, sum formula that tells us how to turn sums into integrals. So just to remind you, 1 over L, n equals n1 to n2, some function f of little n over L, I can write as the integral, when L becomes very, very large, integral dx f of x. And the integration boundaries, I should take n minus over L to n plus over L, where n plus is n2 plus a half, so I have to slightly shift them, correspond to what I have here, and n minus is n1 minus a half. And then the correction terms are 1 over 24L squared, f prime n minus over L minus f prime n plus over L plus dot, dot, dot. Yeah? So this is how you turn sums into integrals and retain knowledge of corrections. Okay? So those of you who know conformal field theory will now be very happy in 1 second, because if we apply this, what do we get? So we get ground state energy becomes L integral minus d over 2 to d over 2 dx. Here I have minus j cosine 2 pi x plus h. So you see the integral now no longer contains any L. Yeah, so this is a number. And then the correction is just minus j pi divided by 6L squared sine pi d plus dot, dot, dot. So that's what comes out here. I just do the calculation. Okay, so this becomes L times E infinity. So this is actually the ground state density in the thermodynamic limit. No longer contains L. And then the correction here is what? So this is pi times the Fermi velocity divided by 6L. And then the corrections would be here order L, 1 over L squared, where the Fermi velocity is just J sine kf. And kf is pi times the density. Okay, what is the Fermi velocity? Well, okay, so if you have this dispersion, so you have filled the Fermi sea between minus kf and kf. The Fermi velocity is basically just the derivative of the dispersion at kf. Okay, so those of you who know conformal field theory, this is exactly the kind of correction you get for conformally invariant theories, and it tells you the central charge is 1. Okay, so it's just an aside, we're not going to use this. And the ground state momentum is what? Yeah, it's 0 because I filled the Fermi sea symmetrically. Okay. Now the rest is quite straightforward. So now the first thing we can do is we can change n to n plus L, where L is even. So we stay in the same sector. So there you can repeat the analysis we have just done, and you find that EL, so this basically would correspond to the ground state, to a Fermi sea, but now with a different fermion number. So EL would be E ground state if you do the calculation plus pi VF divided by 2L L squared plus dot dot dot. Okay, so this is just a variant of the calculation we have done here. Then finally, we can talk about the full spectrum of low-lying excitations. So low-lying excitations come in two categories. Yeah, so here I have K, here is E, E, K. So the ground state is always this Fermi C. Yeah, and what this corresponds to is basically just adding two fermions here. But the kind of more interesting excitations are like these. So I can, let's say, get a low energy excitations by poking a hole here and placing it here. Yeah? And I could also make a low-lying excitation by poking a hole here and placing it here. So that's one class of low-lying excitations I can make. So this would correspond to an extra contribution, E ground state, plus epsilon of K particle minus epsilon of K hole, where I have poked a hole close to Kf or minus Kf, and I have put a particle in the vicinity of the same Fermi point. Or, and the momentum of such excitations is quite small, right? Because you see, you go from here to here, so the momentum should be something like 2 pi over L or whatever, right? But I can make another type of excitation. I can poke a hole here and put my particle here. Okay, again, the energy will have this form, but now the momentum of these excitations will be 2kF or minus 2kF or a multiple of 2kF or multiple of minus 2kF. Okay, but the finite size energies we can calculate very easily because we define low-lying by being in the vicinity of the Fermi point. So we say in the vicinity of the Fermi point we can just linearize the dispersion relation. So we can say epsilon of K is approximately plus minus Kf is equal to Vf K minus plus Kf plus little o of 1 over L, or capital O of 1 over L squared, if you wish. So if you go to higher orders in the Taylor expansion, you see it will involve terms that scale like 1 over L squared, but we are just interested in the energy up to order 1 over L. Okay, so we do this. And this tells us everything. So by the way, when do I stop? 1, okay. Okay, so I'm going to write down now what is the finite size spectrum. It's very simple. So E is L E infinity minus pi Vf divided by 6L plus 2 pi Vf divided by L. Here we have L squared over 4. So L is the number of fermions I've added, just at the Fermi C. And then plus N squared. N is the number of particle hole excitations across the Fermi C I make. And then here I have M equals 1 to infinity, M times nm plus n minus m plus order 1 over L squared. So this nm and n minus m, they're also integers, and they basically tell you how many particle Hall excitations you have made, let's say around the right Fermi point and around the left Fermi point. It's because k squared is the correction to the dispersion. Yeah, so if I go to second order in the Taylor expansion, I get a k squared term. And so k minus kf is 2 pi over L times a small integer. Yeah, and then k squared would be 1 over L squared. Okay? And P is 2 kfn. So as I told you, n is the number of particle excitation across the Fermi sea, plus 2 pi over capital L ln plus m equals 1 to infinity m n m minus n minus m, and little l is the number of particle Hall excitations across Fermi sea, and n plus minus little m is the number of particle Hall excitations around plus or minus kf with momentum 2 pi m over L. Okay, so that is the answer. So I'll show you that in a moment. Now, for L odd, I shouldn't say L odd. So for N odd, yeah, you can repeat everything I just did. Yeah, and it gives you, just a second, it gives you the same answer. The only difference is here, little l was even, and if I consider the sector with odd particle number, little l will be odd. So in other words, if I combine both sectors, I always get these formulas where L is now just an integer. Yeah. This one here, across the Fermi sea. Yeah, because it clearly costs energy, costs momentum 2kf, and you can see here, that's the dominant term. Okay. Now, just to explain a little bit how these particle Hall excitations around the same Fermi sea work. So let's look at an example. With n, 1 is equal to 2. So my Fermi sea might look like this. 1, 2, 3, 4, 5. And then here I have all the empty sides, all the empty momenta. So this would be my Fermi sea. This would be the ground state for 5 fermions. Okay? Now I consider an excitation where I first move this fermion, so the fermion with this momentum, by 1. So I give it a little bit more momentum. And after that, I move this chap here. So that means I've made 2 particle Hall excitations where I have shifted the momentum by 2 pi over L. Okay? So that gives me then a Fock state, which looks like this. 1, 2, 3. This one is empty. And then here I have 2 filled, and then I'm empty. Okay, so that's the notation. All right? So I have 5 minutes, which means I will start the next thing. So now the important observation we can already make. So this is the low energy spectrum. Yeah, so it tells me that the, the low-lying part of the spectrum, they're all energy levels that scale like 1 over the system size, gapless excitations, yeah? And the same with momentum apart from this. This set of levels, yeah, I will now recover by taking the continuum limit of the theory. So this is the same you get as the spectrum of the field theory limit of this lattice model I'm going to construct for you now. It's exactly the same as what we had for the free boson, free compact boson. It's identical. Yeah? The momentum of the free compact boson is almost the same. So what we had for the free compact boson momenta was this part. Yeah? And this part we didn't have. Yeah? And this part will now disappear. It's a lattice property when we go to the field theory limit. And then the result will be we get a fermionic field theory which has exactly the same spectrum as the free boson, suggesting the two theories are the same, and then we will identify operators in one theory with the other theory. Actually, yeah, it probably doesn't make sense to start. I have to stop at 1. Yeah, okay. So I have 3 minutes. If you have a question, you can ask. Otherwise, yeah. Yeah.
I wanted to double check why in case when n is odd, l is odd.
Dot.
L is even.
Which L are you talking about now? Little lowercase, good. Yeah. I thought you were talking about capital L, you know, so which is always even, I mean, by definition. Yeah, so you have to be careful, right? Because we're looking now at one of these blocks. They disappeared now. So the particle numbers I'm allowed to consider must always just change by 2. Yeah? So which is why when I derived this, I said I start with some fixed particle number, then I consider these particle excitations which do not change particle number, yeah, which are essentially these ones here and the ones associated with the n. But then I also had the excitations which did change particle number, but only by multiples of 2. Yeah, that gave me this formula. Now what you're asking, well, what if I want to change it by 1? Okay, so what I need to do is I have to forget about this now, because now I'm in the other sector. Yeah, so I start by computing the ground state energy in that sector. Yeah, and then constructing the same kind of excitations I had here over that ground state. That gives me another set of energy levels. I have now the odd energy levels, the even energy levels. Okay, so I have E even and E odd. So I have all these energy levels, tuck, yeah, whatever. And here I have the odd ones. And I can construct them in exactly the same way. Now what I started with, I said I have chosen my magnetic field in such a way that the overall ground state, the overall lowest energy state, is here in the even sector. So this is the ground state. Oops. This is the ground state. But now I can just combine these two, and I can say, okay, I can now make excitations where I change particle numbers by 2, so this is somewhere here. Or I can add 1 fermion, but then I have to go over here. Yeah? And this I can precisely do, it turns out after the dust settles, by simply taking L to be an odd integer. Yeah? So this is how it combines. All right? Any other question? No, everybody wants to have lunch. Let's have lunch.